Welcome back, everybody. Today we're going to begin with some notation that you may or may not be familiar with. All right, and that notation looks like this. This is the Greek letter sigma. It means sum of. So whenever you see a sigma, we're going to do what we call an iterative process, which means that we have many repetitions. So I'm just going to do I equals 1 to 6 of just plain old I. And basically what this means is I'm going to take the 1, I'm going to run it through my process. Whatever this process is, I'm going to run it through. So right now it's just plain old I. So when I run a 1 through, I get a 1, then plus 2, then I run a 3, then a 4, then a 5, then a 6. And when I add them up, it equals 21. Now this process can be as simple as just plain old I, or it can be more complicated. So we can start our process at 0. 0 plus 1 is 1, so I get a 1. 1 plus 1 is 2. Then 3, then 4, then 5, then 6, and I still get 21. All right? The process can get more complicated because I can do the sum of, and I can change my letter to J equals 3 to 7. So you're not stuck with I. You can do any letter you like. And our process could be like J squared. Then I get 3 squared, which would be 9, plus 4 squared, plus 5 squared, plus 6 squared, plus 7 squared. And if I'm not mistaken, I believe that that adds up to 135. Now, for the more complicated summations, for the easy ones like the ones above, you can just run them through the process. But if you're going from, for example, from I equals 1 to 100 or I equals 1 to 1,000, you really can't run those numbers through a process. It's not really practical. So mathematicians came up with some formulas to help you. So, for example, the first formula says I equals 1 to some number n. Now remember, n is a constant. We just don't know what that constant is in the formula. We're generalizing. And c, again, would be a constant, would be c times whatever your endpoint is. Second formula would be I equals 1 to, again, some number n of just plain old I. And that formula is n times n plus 1 over 2. The third formula is sigma I equals 1 to n of I squared. And that's n times n plus 1 to n plus 1 all over 6. All right, let's just make that better. 2n plus 1 all over 6. The last one is I equals 1 to n of I cubed, and that's n times n plus 1, the whole thing squared, over 4. All right, so these formulas can come in handy with a example kind of like this one. I equals 1 to n of I plus 1 over n squared for n equals 10, 100, 1,000, 10,000. All right, now for 10, you could probably run it through the process, right? So if I put 10 there, you could generate the 10 numbers and then just add them up. All right. Now, this process is really used for when it's 100 or 1,000 or 10,000 because not really practical to say I'm just going to add up all those numbers. All right. So first steps first. We have a constant here. We have a constant in our denominator. So I'm going to take that constant and I'm going to push it out of my equation, out of my summation. And I'm left with I plus 1. Now, what I can do is I can take that I plus 1, and I can say 1 of n squared, sum of I equals 1 to n of I, plus sum of I equals 1 to n of 1. All right, so now we have some formulas, right? This right here is a formula. I think it's formula number 2. Yes, see? So I can do n times n plus 1 over 2. And 1 is a constant, so that's formula number 1. C times n. All right, so if we substitute in our formulas, I get 1 over n squared times n plus 1 over 2, and that one would just be plain old n. All right, and we're pretty much where we need to be. All right, so from here, it's just a matter of simplifying just a little bit. So for example, in my parentheses, I could make a, I could distribute here and then make a common denominator. So I get 1 over n squared, and that's n squared plus n plus 2n all over 2. You're welcome to check my work. And that's 1 over n squared times n squared plus 3n all over 2. And then I can pull out an n, right? So I get 1 over, here, 1 over n squared times n plus 3 all over 2. So I get, my final answer would be n plus 3 over 2n. And now from here, you're welcome. You could not only plug in 10, which wouldn't be so bad, but you could also plug in 100, 1,000, and 10,000 and get the numbers that you need. All right, so in the last unit on derivatives, we said that derivatives represent the slope of the tangent line. All right, integrated, we started last section, we said represents the area under the curve. All right, so I want to talk about how we're going to estimate the area under the curve. We'll come back to summation notation, if not in this section, definitely in the next one. But I just want to start with this. So I get, so here's, the best way to do it is with an example. Negative x squared plus 5. And basically what I'm going to do is, we're going to do this 2 different ways. All right, so I'm just going to start by graphing it. All right, and I'm just going to graph in the first quadrant. So I get 1, 2, 3, 4, 5. There's my vertex. And then I have 1 and let me fix that. All right, so 10/5 would be 2. So this would be 1, 2, 4, and 5. And we have a point there, and we have a point here. Because if I plug in 2, 2 squared is 4. Negative 4 plus 5 is 1. That's how I got that point. So that's 2, 1. And if I plug 0 in for x, 0 squared is 0 plus 5 gives me 5. So those 2 points I generated from the equation. Now you can technically generate as many points as you'd like. All right. For this particular problem, all I need really is 2. And then I'm just going to try to make a nice sketch of an arc right there, because the graph is really just a visual. All right. And basically what we're going to do is this, is that we're going to find this area under the curve without calculus. And the reason we're going to do it without calculus is because we don't know how to do a definite integral just yet. We just talked about indefinite integrals. And I want to see if we can figure out a way that we can get as much area under this curve using some knowledge that we already know. Now, the knowledge we already know is we're going to create rectangles. The reason that we already know rectangles, all right, is that, hang on. Oh, things went awry. Let's just put everything back the way it was. Okay, so there we go. All right, not the greatest in the world, but it'll work. And again, this is just an estimate. So that's just under 5. And then I can go up here like this and go like this. And what we notice is that not only do we know the area of rectangles, but if I put enough rectangles in here, I'm getting an awful lot of my area. Now, this first technique we're going to call right endpoints. And that's because the top right of my rectangle lands on the curve. Now, this is not a perfect estimate of the area under the curve. The reason it is not a perfect estimate is what we notice here is that the blue is the unused area that we have. So this is technically an underestimate. All right. Now, the other way we can do this is we can make a graph, and I'll make the graph in green this time, just because I can, no special reason. And again, I'm going to do it the same way. All right. Same type of thing. So I'll use blue to give contrast. There's my point, and there's my point. And I can just do a nice arc down. And we'll make nice blue rectangles, just because I can. That's not what I wanted to do. I wanted to do this. Now notice these rectangles are attaching to the curve at the left endpoint. It's okay if it's not perfect. I've never been the best drawer of graphs, but as long as you do your best, that's all I ask of anybody. But what we notice here is that these rectangles are larger than the curve. So we can call these left endpoints because they attach to the curve on the left. And this is going to be a slightly over estimate. All right. So now The reason we're using rectangles is because we know the area. All right. So I'm going to scroll back up. We're going to start with our right endpoints, and we are going to try to work out our estimate of what the area is going to be. So let's start here. Let's start with area equals the length times the width. Now the width of each rectangle is 2/5. I made it 2/5. I have 1, 2, 3, 4, 5 rectangles. So I apportioned it off by fifths. That way I could make nice, even widths. That's really essential to getting a good area, is to not have varying widths. So, so 2/5. Now for my right endpoints, right, I now need to know my height. And my height is here, or my length is here, depending on whatever you want to call it. So how do I get this point on my curve? Well, I take 2/5 and I plug it in to my function to get the y value. So it's 2/5 times f of 2/5. Don't need so many parentheses. Plus 2/5. Now I need the next height. Now if I look on my graph, right, I have to go up to 4/5 and then go up to whatever y value 4/5 is. So it's going to be f of 4/5. Now my third height is going to be f of 6/5. Times f of 8/5. (10/5) or 2. All right, so now remember, our function is there it is, and our width is 2/5. All right, so at this point I'm going to pause the video, and I want you to evaluate this statement. All right, there are going to be a lot of fractions, so take your time, and we'll correlate our answers on the back end. All right, so hopefully you were able to work this out by taking 2/5, plugging it in, 4/5, plugging it in, so on and so forth. I got an answer of 162 over 25. That's a perfectly acceptable answer. Or if you wanted to, if you're able to put it into a decimal form, you could say it would be 6.48. And this is an underestimate of your area. Some of the area under the curve is not included. All right, now in order to know, the upper estimate of your area, you need to do your left endpoints. So again, our width is still, I'm going to change color just for contrast. I'll go to blue. There we go. Our width is still 2/5. However, what we notice is that by using our left endpoints, now I need to go f of 0 to get the y value. I need to go f of 2/5. So our y values are just shifted over 1. So it's 2/5 times f of 0 plus 2/5 times f of 2/5 plus 2/5 times f of 4/5 plus 2/5 times f of 6/5 plus 2/5 times f of 8/5 plus 2/5 times f of, wait, hang on, 1, 2, 3, 4, 5. Perfect. I don't even need this one. Remember, we have 5 rectangles. So let's go back up. Now, this is why it's really important to have your graph handy, because again, there's f of 0, there's f of 2/5, 4/5, 6/5, and 8/5. That covers 1, 2, 3, 4, all 5 rectangles. Now, this is going to be more area than we need. However, what I'd like you to do is to evaluate this statement. I'll just make it a little bit bigger, and then we'll correlate our answers on the back end. All right, so hopefully you paused the video to work this out. Again, my function is negative x squared plus 5. All right, so if you didn't, take an extra moment, pause the video to work it out. However, I got an answer of 202 over 25, or if you're able to convert to decimals, 8.08. For me, the fraction would be fine. And so we can say, and I'll just do it with decimals because it's easier. So our area is in between 6.48 and 8.08. Now, you might say, well, that's a pretty decent range, right? We're only within less than 2 getting our area, but what if we wanted to improve our estimate? How would we do that? Well, you would do that by using more rectangles, because if you notice on our graph, right, let's say I wanted to put another rectangle like here, right? Then less area would be extra, right? So more rectangles means better estimate. So in this particular problem, I'll let you know that if you happen to split this up, not just into 5 rectangles, but to 25 rectangles, see how less area is used? So here even I can do this, where I can go out like this, and then up, right, and then out like this. And then you see how less area is unused, the more rectangles we put in. If I took it out to 25 rectangles, and I'm not going to do the whole problem here, all I'm going to tell you is that if we use 25 rectangles, our area would be in between 7.17 and 7.49. And we notice that our estimate dramatically improves to less than half a point. All right. So basically, what the summation notation is, now I'm going to put both together. The summation notation allows it so you don't have to write out this whole string. Now, for 5 rectangles, even for 8 rectangles, I always found it easier just to write it out. However, if you wanted to write this out with summation notation, you could write it out I equals 1 to 5, because there's 5 rectangles. And our width is 2/5. And our height would be f of 2i minus 2 over 5. All right, and this works. So you could write it like this, then you could generate the numbers or use the summation formulas. All right. So let's try another example. All right, so the example is find the area of the region bounded by the graph of f of x equals x cubed, the x-axis, and x equals 0, and x equals 1. All right, so let's check out how to do this. Well, the first thing I want to do is I want to sketch a very quick graph between 0 and 1. There we go. And we're going to do rectangles. All right. So now I want to figure out how to do some summation notation. And notice I didn't specify how many rectangles. So I want to do as many rectangles as I can to get as good an estimate as I can. So I said in the last problem, the more rectangles I use, the better. All right, so what's the best? Well, the best would be to take my rectangles out to infinity. Now, we can't count to infinity, but we can take the limit as n approaches infinity, right? And I can sum I equals 1 to n, all right? And now I need my, my width is going to be 1 over n, right? Because that's the spacing. And then my height is going to take that and I'm going to plug it into x cubed, but I need to move it along. So I need an I, otherwise it's just going to be a constant over n, the whole thing cubed. All right, so this is going to move it along ever so slightly, and it's going to allow us to get this area as good as we can get it. All right, so we're going to need to probably use some of these formulas that we wrote out before. All right, so of course this should be a cube, not a squared. All right, so if I cube this, I get n cubed on the bottom times n. So I'm going to pull out my constant, 1 over n to the 4th. And then I'm going to be left with the limit as n approaches infinity of I cubed. Now I cubed has a formula to it, right? Or hang on. Sum I equals 1 to n of I cubed. My bad. So I have 1 over n to the 4th. Now I want to apply the formula, so I have the limit as n approaches infinity, n squared times n plus 1, the whole thing squared, over 4. Now we got to do some algebra, because the n plus 1, the whole thing squared, could be multiplied out. All right, and then you got to distribute your n. So let's do that real quick. So I got 1 over n to the 4th, limit as n approaches infinity, n squared times n squared plus 2n plus 1 over 4. And then when I do my distributive property, I get 1 over, actually I can bring that back in now because because now we want to evaluate that limit. So I'm going to distribute. So I get n to the 4th plus 2n cubed plus n squared over 4n to the 4th. Now I can simplify each one of those fractions, okay? So I get the limit as n approaches infinity. N to the 4th over 4n to the 4th is just 1/4. 2n cubed over 4n to the 4th. I get 1 over 2n. And n squared over 4n to the 4th, I get 1 over 4n squared. And now when I take my infinity and I plug it in, I get an answer of 1/4. All right, so that's where we're at. There's a lot more practice to go. This is just a precursor to definite integrals. So there will be a slightly easier way. But for now, that's it. Thank you for listening, and I'll see you all next time.